What's going on, guys? I just wanted to take a second, go through the review problems with you guys to make sure you guys have something to look at for our assessment, which is coming up in, I guess, today or tomorrow, depending on when you take it. Now, the review here is not necessarily in order. I randomized the questions, which means when I was going through it, the questions were probably in a different order than when you're going through it, so you might have to look around a little bit. And this is probably going to be a long one because it's 26 questions. It means we're going to have to do a little bit of math. So this will probably be a long one. You don't necessarily need to watch the whole thing, but if you want to jump around, try and find the ones that you had questions about, I think it should be pretty easy for you to figure out where you need to be. All right, so I'm just going to go ahead and start. Go through the ones that I have in the order that I have them, and then I'll post this on our Schoology page so you guys can check it out. So first question, when an object becomes negatively charged, does its mass increase, decrease, or stay the same? Right? And then this is a multiple choice question. It had those options, increase, decrease, or stay the same. So what we need to look at here, right, is what happens when something becomes negatively charged. So in order to become negatively charged, what has to happen? And in order to become negative, right, an object has to accrue more negative charge in terms of electrons. So in order to become more negative or to become negative, an object has to gain electrons. And if an object is gaining electrons, what's going to happen to its mass, right? It's gaining matter. Electrons are matter. So if it's gaining electrons, then the mass has to increase. Right? So when an object's becoming negatively charged, it actually gains electrons and its mass increases. The converse of that is true for when things become positively charged, right? In order to become positive, an object has to lose electrons, right? That's how things become positive. They have to lose electrons. And if an object is losing electrons, it's losing matter, it's losing mass, its mass decreases. So when an object becomes negatively charged, its mass increases. When an object becomes positively charged, its mass decreases. But this question was about negatively charged, so its mass increases. 2, the attractive force between a charge of 8.44 microcoulombs and Q is 0.957 newtons when the separation between the charges is 1.31 meters. Find the charge Q. So we know Q1, we'll call it, is 8.44 microcoulombs. We have Q. We don't know. We have the force is 0.957 newtons. And we have the distance, right? The separation distance is 1.31 meters. So this is just going to be a straight Coulomb's law equation or Coulomb's law problem. F equals K, Q1, Q2 over R squared. We should probably also put down here that K equals 8.99 times 10 to the 9th. So F is 0.957. K, I'm going to run out of space for sure. 8.99 times 10 to the 9th. Maybe not. 8.44. Now this is microcoulombs, right? So we have to remember to add in that times 10 to the negative 6th times Q. Cutting it close. Divided by R squared, which is 1.31 squared. So now we just got to do some algebra. We got to solve. Let me get out a calculator here. I'm going to start by multiplying both sides by the 1.31. So 0.957 times 1.31, squared will give us 1.6423, whatever, equals, we can multiply these two together. Now, depending on whether you have a scientific calculator or not, a little bit of difference. I'm going to assume some of us do, so 8.99 times 10 to the 9th times 8.44 times 10 to the -6th gives us 75,875.6 times Q. And then to solve for Q, we just got to divide the other side. So we'll take that 1.6423077 divide by, I just pulled that from right here, the 75,875, and we will get Q is equal to 2.16 times 10 to the -5th coulombs. Let me pull up the answers here, see if it's... I can't find it. Where'd it go? Nah, we'll pretend I'm right for now. All right, so we get this right here, which I think I rounded to 2.2 times 10 to the -5th coulombs in the problem. So there is the second problem. A little bit of math. It's good for us. All right, number 3. System consists of electrons and protons. The system contains 5 protons and has a total charge of -2e. How many electrons are in the system? So -2e means that there are two extra, or I guess to say 2 more electrons than protons in the system, right? It means the electrons are winning by 2, right? If we have a charge of negative tells us the electrons are winning, 2 tells us by how much, right? The E just tells us that we're talking about electric charges. So the electrons are winning by 2 in this system. So if we have 5 protons, and we know the electrons are winning by 2, how many electrons do they have to be? Well, there has to be 7 electrons, right? If we combine those, that would give us 2 extra electrons, which would give us a total charge of -2e. All right, so there are 7 electrons in that system. Number 4, what is the size of the electric charge on an electron? This one, you just got to memorize. It's just talking about the size, so we're not worried about positives or negatives. So we just want the number. An electron is 1.6 times 10 to the -19th coulombs. Just something we got to memorize, right? That is the charge of an electron, right? Electrons would be negative, protons would be positive, but they're both the same size. When charges interact, number 5, like charges attract and opposite charges repel. This was a true or false. And probably one that we should be pretty familiar with because we've heard that opposites attract our whole lives. But this says like charges attract, opposite charges repel. which is false, right? We know that opposite charges attract and like charges repel. So this one is false. That is not correct. It is actually the exact opposite of that. Match the particle with the charge. All right, I think this one hopefully was pretty easy. Protons have a positive charge. Electrons have a negative charge. And neutrons have no charge. Ooh, CHRG. They're like the one thing that we can say has no charge, right? Neutrons don't have any charge. Not even do they have just balanced charge, neutrons have no charge. So that one hopefully was pretty easy for us. Just another thing we gotta memorize, right? Number 7, state whether the following charges are possible because of charge quantization. So, charge quantization tells us that everything has to be a multiple, or all charges a multiple of 1.6 times 10 to the negative 19th, right? Coulombs. Because this is the charge of an electron and the charge of a proton, and protons and electrons are the smallest things we can have, every charge has to be a multiple of this number. So to check that, all we have to do is divide these by 1.6 times 10 to the negative 19th, and if they go in evenly, right, if we get a whole number, then it's possible. If they don't go in evenly, we don't get a whole number, then it's not possible. So 3.2 times 10 to the negative 19th divided by 1.6 times 10 to the negative 19th, we get 2. So that is possible, right? That's a whole number. It goes in evenly, so that one's possible. 4.8 divided by 1.6 times 10 to the negative 19th, that gives us 3. So that one's possible, right? Another whole number, it goes in evenly. That works. 5.2 divided by 1.6 gives us 3.25, which is not a whole number, which means 1.6 does not go into 5.2 evenly, which means this is not possible. Right? We would have to have a quarter of an electron in order to make that charge possible, and we can't have quarter electrons or quarter protons because that is as small as things get for us. 6.4, we get 4 when we divide 1.6 into there, which means that is definitely possible. So possible, possible, not possible, possible. If it's divisible by 1.6 times 10 to the negative 19th, then it is a possible charge. If it's not, then it is not possible. Find the electric force between the charges 0.12 coulombs and 0.33 coulombs at a separation of 2.5 meters. So another Coulomb's law question. Don't know the force. Q1 will be 0.12. Q2, 0.33. Separation distance, 2.5. And a K value of 8.99 times 10 to the 9th. So we start with Coulomb's law. F equals K Q1 Q2 over R squared. We plug in what we got. 8.99 times 10 to the 9th. 0.12. 0.33 divided by 2.5 squared. Let's multiply across the top first. 8.99 times 10 to the 9th times 0.12 times 0.33 gives us 35600 divided by 2.5 squared gives us 6.25. And then we just got to divide there. So we take our 356,004,000 divided by 6.25, and that will give us a force of 569,60640. Now, this probably, at least the way I did it, this will not show up on any of the solutions, right? This is not one of the answers, this full number. The answer is in scientific notation, which means we need to change this so that it is in scientific notation. So scientific notation, we want to take the decimal, which was here, and move it 1, 2, 3, 4, 5, 6, 7, so that it's right after the first number. So we should get 5 point, we'll round here, so 69 would give us 7, times 10 raised to the number of places we move the decimal. So 1, 2, 3, 4, 6, 7 newtons. And that should show up in our answer somewhere. Let me see. Make sure I did that right. Why can't I find these? There it is. Does that show up? 5.7 times 10 to the 7th. Yep. So our force is 5.7 times 10 to the 7th newtons. When an object is positively charged, and then we get a couple of statements, right? When an object is positively charged, which one of those statements is true? So I think the statements were, it has more protons than electrons. Right, it has more protons than electrons. Well, if an object is going to be positively charged and protons are positive, right, P, E, then it definitely should have more protons than electrons. The second statement was it has more electrons than protons. All right, if it had more electrons than protons, then it would be negatively charged, so that is not correct. One of them was it has equal number of protons and electrons. Well, if it has an equal number of protons and electrons, then the positive and negative charges will be canceling out, and we'll get a total charge of 0. So that one can't be right. And then the last one is said it has more neutrons or protons than neutrons, which could technically be true, but doesn't have to be true, right? The proton and neutron interaction and the comparison there has nothing to do with whether it's going to be positively charged. It has more to do with like nucleus stability than it does with charge. So this doesn't matter a whole lot. So the only thing that matters is that it has more protons than electrons. Match the particle with its mass. So this one, we got a couple masses, and we had just matched. So I'm just going to go through. An electron has a mass of 9.11 times 10 to the negative 31st kilograms. A proton has a mass of 1.673 times 10 to the negative 27th kilograms. And a neutron has a mass of 1.675 times 10 to the negative 27th kilograms. That one's just something we got to memorize, right? Mass of the electron, mass of the proton, mass of the neutron. All right, system contains 72 electrons and 45 protons. What is the total charge of the system? So, this one is actually pretty easy. It might sound a little bit hard, but the way that we answer the question is pretty easy. So, if we have 72 electrons and 45 protons, right, we want to look at the total charge there. Well, 72 electrons will contribute to negative charge. 45 protons will contribute to positive charge, right? Positive tells us we're talking about protons, negative tells us we're talking about electrons. The E just tells us we're talking about charge. So what's our total there, right? We do a little subtraction or addition, whatever you have, and what we're left over with is negative 27 E. So the total charge there is negative 27 E. Now, if we wanted to actually figure out the charge in coulombs, right, as opposed to just number of electrons and number of protons, what we would do is take this negative 27 and multiply it by E, which stands for the charge of an electron. Well, we'll just write 1.6 because the negative is already there, times 10 to the negative 19th. And if we multiply this by negative 10, or negative 1.6 times 10 to the negative 19th, it'll give us the charge in coulombs. So 27 times 1.6 times 10 to the negative 19th. If we wanted the charge in coulombs, it would be negative 4.32 times 10 to the negative 18th coulombs, right? But problem doesn't ask us to do that. It just asks us to leave it in terms of E, right? The number of electrons and protons. So we get that negative 27 there. Number 12 is a long one. All right, so 3-point charges lie on the x-axis. We have charge 1, which is negative 2.1 microcoulombs, charge 2, which is 3.2 microcoulombs, and charge 3, which is negative 1.8 microcoulombs. We want to determine the direction and force on charge 1. So we want to focus on charge 1. So first thing I want to do is just decide which way the other particles are exerting their forces. So Q2 is positive, Q1 is negative. So which way will Q2 apply a force to Q1? Well, opposites attract, so it's going to apply an attractive force, meaning it's pulling Q1 towards it. So the force on Q1 by Q2 will be to the right. We look at Q3. Q3 is negative. Q1 is negative. They're opposites, so they're going to repel, which means Q3 is going to push Q1 away. So force on Q1 by Q3 is going to be to the left. So that tells me which one I'm going to add and which ones I'm going to subtract when we get to kind of after we've solved for everything. So F13 will be negative, right? The force on charge 1 by charge 3 will be negative. The force on charge 1 by charge 2 will be positive. So now we just got to go ahead and solve for our forces. I'll start with F12, right? Force on charge 1 by charge 2. So Coulomb's law, F equals K Q1 Q2 over R squared. 8.99 times 10 to the 9th times 2.1. Remember, these are absolute values, so we don't have to put in the negative sign. And actually, we should just realize, right, this is going to be positive. We can leave it positive the whole time. Times 10 to the negative 6th times 3.2 times 10 to the negative 6th. Right, we got to get that negative 6 in there because they are both in microcoulombs. divided by the distance, which is 7.5 centimeters. We need that in meters, so 0.075 squared. All right, we can do all that. Put it in the calculator really quick. We can actually do it all at once if we're good with our parentheses. 8.99 times 10 to the 9th. I'll use this times 10 to the 9th times 2.1 times 10 to the negative 6th times 3.2 times 10 to the negative 6th divided by 0.075 squared will give us 10.74 as the force. Now I did that all at once. That is certainly something that you can do when you start feeling confident. If you don't have a graphing calculator and you need to multiply that all out individually, that's fine. It might just take you a couple seconds longer. But you should arrive at the same answer. Let's do F13. We'll start it up here. This one's going to be negative, right? We decided it's going to be negative. So negative K Q1 Q3 over R squared negative 8.99 times 10 to the 9th. Am I going to run out of space? Look at that, definitely. 2.1 times 10 to the negative 6th. 1.8 times 10 to the negative 6th. I made it fit, not really well, but it works. Divided by the distance here was 11 centimeters, so we're going to make that 0.11 meters squared. Again, we can plug that all into our calculator. 8.99 times 10 to the 9th times 2.1 times 10 to the negative 6th times 1.8 times 10 to the negative 6th divided by 0.11 squared, equals, I messed up, classic. Oh, I didn't put a parentheses at the beginning. Whoops. Gives us 2.8. So our force 1.3 is negative 2.8. So when we combine these, right, because we do want to add them together to get the total force, we're going to get the total force will be 10.74 minus 2.8, which will give us a force of 7.9 newtons. Still positive, right? The 10 positive force is going to outweigh the 2 negative force, so we get 7.9 newtons as the total force there. All right, that's probably one of the harder ones on the page here. So take a couple of looks at that because this will show up again. All right. (13) The charged rod is brought near a suspended object. The object is repelled by the rod. Based on the interaction, we can conclude the suspended object is charged. And I believe this was another true or false. And these ones might seem easy, but there's a little bit of extra thought there that we need to go through. So if an object is repelled, right, what do we know about things that are repelling? Repelling things are like charges, right? So positives repel positives. And negatives repel negatives. So on the surface looking at it, right, if we have something that's going to be repelled, then it either has to be positive or negative, right? If the charged rod is positive, then the object is positive. If the charged rod is negative, then the object is negative. And that's true. All right, for repulsion, for things that are repelling, that is absolutely true. If we get a repulsion, then both objects have to be charged. The tricky part comes in when we're talking about things being attracted, which I think I asked a question about, so I'm going to leave explaining that for a little bit. But when we're talking about repelled, when things repel, then they absolutely both have to be charged. So for the repulsion one, that is true. All right, 14. Two identical charges experience a repulsive force of 1.9 newtons when their separation is 1.2 meters. What is the value of each charge? So we've got Q1 that we don't know. We've got Q2 that we don't know. We've got K, 8.99 times 10 to the 9th. We've got F is 1.9. And we've got R is 1.2 meters. Okay, so it's another Coulomb's law one, right? F equals K, Q1, Q2 over R squared. We plug in what we know. 1.9 equals 8.99 times 10 to the 9th times Q1 times Q2 over 1.2 squared. And right here, it might look like we're in trouble because we have two variables in one equation, right? And we can't usually solve for something if there's two variables in the same equation. We need to just have one. But the nice part about this one is we know that the charges are identical, which means they have the same value. So we could just easily say, okay, well, instead of writing this as Q1 times Q2, where I have two variables, let me just make this one Q1, right? Because Q1 and Q2 are the same size. If we solve for one, we solve for both. Now I have only one variable, and I can go ahead and I continue solving. So 1.9 equals 8.99 times 10 to the 9th times Q1 squared, right? Because Q1 times Q1 is Q1 squared, divided by 1.2 squared I can do. I should have known that, 1.44. All right, and now we're just solving. So we need to get this out of the denominator, so we multiply by 1.44 on both sides. That will give us 2.736 equals 8.99 times 10 to the 9th times Q1 squared. We divide by 8.99 times 10 to the 9th. That'll give us 3.04 times 10 to the negative 10th equals Q1 squared, and then we take the square root of both sides, and we get 1.7 times 10 to the negative 5th coulombs, right? And that just solves for Q1, right? But since Q1 and Q2 are the same, we've solved for both of them. So the problem's over there, right? Nice and easy. Let me check to make sure that's an answer. Two identical charges. 1.7 times 10 to the negative 5th is there. Excellent. All right, so there is